Abstraction. My name is Jon Peck. I work for Algorithmia. I am trying out this new title, full spectrum developer. What do people think? The idea, yeah, good, okay, cool. It's beyond full stack. I do a little DevOps. I do a little other stuff on the side. And I do advocacy, so I get to go out and talk to fun people about what we do and find out all your problems and then bring them back and make our stuff work for you, which is the awesomest job in the world. If you're a developer now and you ever get to the burnout point, I completely recommend moving into advocacy after. It's wonderful. Algorithmia, all right, our little line, making state-of-the-art algorithms discoverable and accessible to everyone. It's a really tight way of saying we make it possible for any developer anywhere to use machine learning in a really simple, easy-to-use way. So you can come on to our site. You can say, I want to do automatic colorization of images. I want to do detection of objects in the photos that I send you. I want to do some advanced natural language processing and extract meaning from some piece of text. And instead of you having to go and train that up, and I'll talk a little bit about model training and that sort of thing in just a second, you can just go and you can just copy and paste a code snippet in whatever language you're working in, and boom, it works from where you are. The flip side of that is, if you are a data scientist and you're building your own models, or you're a company that's building models internally, you can take those models, you can put them up into our system, and they pretty much just work, which is cool. You upload that model, you write a few lines of code that's going to wrap that, deserialize it, do the prediction, return a result. You get automatic JSON wrappers around it. You get documentation that's published out to other users. Other people can find it. If you want to, you can put a royalty on it so that you get paid for the research you've done when someone else goes and uses your algorithm. And if you're a company, you take that whole infrastructure, you make it private, you put it on site wherever you are, and you increase your operational efficiency from about 20% to about 80% because you're just using the virtual machines that you're standing up from wherever that much more efficiently. By packing them close, you get elasticity, et cetera. Okay, that out of the way, I'm going to talk a lot more abstractly about this concept that I call an operating system for AI. Before I do that, I should point out, by the way, bit.ly/heavyai, all lowercase. If you want a copy of these slides, go ahead and grab them from there. I'll repeat that again at the end, so you have it. As well as my contact info, I'm Peckjon, Peckjon, on just about every media presence. The advantages of just using my name instead of some groovy handle, right? So you can find me there. Please connect. I love to talk. Okay, so right now, machine learning is really, really popular, right? Huge growth. Every startup in the world is like, hey, we're doing machine learning for X. Some really are, some aren't. For those that are, things start out usually like this. You've got a couple of models, you've got a couple of frameworks that you're running them in, a few languages, and initially you're starting by putting together some dedicated hardware where you're taking that model, you're standing up, say a wrapper, a Flask wrapper around it, you're putting it out there. Your IT team is maybe doing it for you if you don't want your data scientist team to have to learn all about web dev. And you've got a pretty high time to deploy. So from where that data scientist goes and trains that model to where it actually gets live on the web can be a period of a few days, or it can be a period of a few weeks, all depending on where you're going. And that works pretty well, so long as you've just got those couple models, you've just got a few end users, and you are okay with having these heterogeneous APIs where every different model has a different API structure, so then your team has to go and document that and explain it to everybody. Machine learning has these two different sides. It's got the training side, where you're pulling in the data, you're figuring out what it is you want the machine to learn, you're cranking through, and you're letting the machine figure out how to interpret that data. That's a really big simplification, right, of course. But as the very simplest example, hot dog, not hot dog, right? You feed it a bunch of images, you say these are images of hot dogs, these are images of things that are not hot dogs. Over time, the machine learns over much data. And what you come out with is a machine learning model, which is this thing that you can use in whatever framework you're working in, where later on I can say, here's a new image you've never seen, hot dog or not a hot dog. Okay, great, give me an answer, right. So training has this really long time that you're actually going and you're processing through that data. And then the second phase of that is prediction. Once you have that, that's this bit I've been talking about, where you take it, you wrap it up, you make it available to the outside world, and some application somewhere is like, okay, I've got an iPhone app, take an image of something, what is it, send it out to the service, get back a prediction. That occurs over a short period of time. We'll talk more about the characteristics for those in just a second. So what we see with these companies that are developing their own machine learning models in-house, they start out with that pathway, standing up their own servers, that sort of thing. Eventually they hit a level of complexity. And this is the kind of situation that we have run into and we've developed infrastructure for handling, right? You've got, say, 5,000 different algorithms, different models written in heterogeneous frameworks written by different individuals doing different things. Each of those may even have different versions, right? So on algorithmia.com, for example, which is our public marketplace of algorithms, there's about 50,000 different versions. 50,000 different models times versions, right? Average of 10 versions each. We keep those all live so that you can go back to old versions and execute them. That way you don't break your application by deploying something that's not backward compatible, right? We've got now up to about 75,000 algorithm developers. And what they put out there is entirely up to them because we're not a company that has a single business purpose. We're a company that provides infrastructure that lets people bring in their own algorithms. So we have no idea what frameworks people are going to be using at any given time except by looking at patterns of what people have put up there. And each of those algorithms, it might be called once a year, or it might get called 1,000 times per second. And there's really high variance. And this is where it starts to break down for individual companies doing their own hosting, is they have to start predicting what kind of load they're going to have. They have to scale up to that elasticity and then run into problems. Automatic deployment and discoverability, so that when you put that machine learning model out there, you don't have a long pathway from your data science team to your implementation team. We want to bring that down to a couple seconds instead of a few days. We want to maintain low latency on all of those, so 15 millisecond or lower overhead every time you make a call to an API. And have a common API across all of them to allow for composability, which I'll talk about a bit more in a second, and fine-grained security. So, in total, what we're looking at here is we need something akin to an operating system for AI. We want to build a function as a service for machine learning, for deep learning. We want to have a discoverable live inventory of AI, where you can go out and you can say, what's the thing I want to do at this time? Does it exist in the system? Can I find it? Can I compare it to other models that do similar things and decide what's best? Anybody can go and contribute to that. Anybody can use it if you've made your model public. These are composable, so you can move from one model to another seamlessly and pipe the output from one model into another and get a consolidated result. Monetizable with a royalty on top to incentivize data scientists to build new models. And anyone out there in the world can then go and utilize those and make their own applications much, much cooler, much, much faster without having to do novel research on their own. Let's look at the history of operating systems in general to understand why this analogy makes sense of having an operating system for artificial intelligence, right? In the 1970s, we started out with punch cards. And you pretty much, obviously very annoying to code, but then you're tied to a particular system, you're tied to a particular program that's been coded once. You want to go back and change things, you got to write it all over again, print out a bunch of cards, boom, run it into a specific machine built for just those kinds of cards. Off you go. Unix comes along. Multi-tenancy, right? So now I can have multiple different users on the same system running different things, obviously a huge bonus. Composability, the ability to run one program and have its output piped directly into another, so now I can create strings of programs working together in a very effortless way. DOS comes along. We get good hardware abstraction over a large number of systems. You're no longer thinking about, am I writing to a tape device? Am I writing to a network? Am I writing to a disk? I just say file.save and give it an indicator of where it's going, and the operating system does it for me. I no longer have to worry about, am I using a processor, processor was an issue. Am I using a drive created by one company or a physical drive created by a different company? Those just interoperate through the same abstraction layer, right? So we're seeing what's happening here. We're getting better and better abstraction layers over time that make it much easier for the person actually writing the apps to utilize the system without having to make it specific. GUI comes along. And this adds UI multi-tenancy, right? So now I can not just be running multiple programs, I can actually see them both at the same time, see their output, see how they might be interacting. And then this is kind of a weird chump, but when people think about the evolution of operating systems. The big thing, at least to us, about iOS and Android is that the App Store, right? Because now you've got this device, it does some things, and whenever you're like, I want to extend the capability of that device, I want to do something cooler, more interesting, it's no longer go out and say, search the web, find some developer's program somewhere, pay for it via whatever mechanism they have, pull it down, run the installer, wait for the installer to complete, fire up the application, see if it meets my needs or not, right? Now you have app discoverability built right into the operating system. If I search for something in iOS, even if I'm not in the App Store, if I just go and I search across the system for something I want to do, one of the suggestions that's going to come up is, hey, there's this app that might satisfy that need. So I go and I pull down that app, and I have it installed, usually within a matter of seconds, and I'm doing whatever the thing was I wanted to do. So this is a huge evolution, actually, in terms of how operating systems work. We want to do that same thing for AI. What happened with general purpose computing is that you had this long evolution, right, starting in the 70s, even a little before, where we're basically discovering what are the problems we need to solve, what are the abstraction layers we need to create in order to increase overall productivity. So it's much faster for the end user, and it's much faster for developers. So an operating system does just that. It provides common functionality that's going to be needed by all of the programs that might run on it through an abstraction layer. It standardizes the conventions on those so the systems are easier to work with. Again, I just file write. I don't care where it's going. It prevents that high-level abstraction over the underlying hardware, so I'm no longer thinking about what am I even physically running on. Sometimes it's a local machine. Sometimes it's a virtual machine somewhere. I don't care. How are we going to evolve AI along those similar types of evolution to make it work really well for everyone? I talked about those two distinct phases. You've got the training phase and you've got the inference phase. AI in general uses lots of processing power, though the way it uses it in each different environment is different, training versus inference. Inference just meaning prediction, just meaning that phase where I give it a novel image and I say, what does it mean? It can run on heterogeneous hardware, so you can run many things on CPU, but then for certain types of models, they run a lot faster on a GPU system, but there's other things too. There's FPGAs, there's TPUs, there's new kinds of processing units coming down the pipe. And we want to be able to abstract over all of those without having it be really specific when you write the program what it's going to run on. It's limited usually by compute, not by bandwidth. So even if I'm sending moderately large stuff like images, the actual compute time often dwarfs that. So I'm a little more concerned about my compute elasticity. All of this, and what a friend of mine likes to say is that TensorFlow is open source, but scaling it is not, right? So you can go out, you can find a repo to do whatever model you want, you can build it out, you can use things like TensorFlow in order to create those models. And that all is moderately well documented. It's something you can do on your own. The quality of it varies with what data sources you have and what processing you have available. But actually being able to scale, that's not something you can do just at home for free by playing around. It requires real hardware. It requires it actually runs somewhere. It requires time and money and the electricity to make all of that happen. How can we improve? So we'll look at this one use case, right? Yes. We're going to write this app, Seafood. It, of course, is going to do hot dog or not hot dog. We're going to go through this training phase. So what are the characteristics there? There's a really long compute cycle. Usually in the training phase, that's just as much compute as I can do until I'm done with my training run, right? There's ways to do training on multiple units and that sort of thing, but most of the time, you're just taking that fixed execution, as much power as I can get. I'm usually running it as a single user on a single system to do that training phase. And of course, it's stateful, right? So at the time when I'm done, I get some result. In this case, the result is the trained model, and I save that thing, and then I utilize it in the future. This is kind of like the dev tool chain, right? Where I'm actually building my application, right? And then I compile, and I get my application, and then I'm ready to do something with that app. So we do just that. We train up our model, we give it a bunch of images, we get our thing that can recognize hot dog or not hot dog, we put it up on a GPU-enabled server so it runs pretty fast, running TensorFlow underneath, great. Okay, we start utilizing that. And that works wonderfully until our app goes viral and everybody in the world is using it, And of course, predictably, what happens is the server crashes and burns at that point, right? It simply stops serving requests, or I have to go and I have to manually scale new server instances, whatever's required to satisfy that load that I didn't predict for, right? And even if I had predicted for it, how much money am I willing to spend up front to guarantee that I won't have that problem when the actual usage goes really high? Okay, so let's take a look at the inference phase and its characteristics. Really short compute bursts. Intense sometimes, but very short. Give me one image, give me a result for it, as fast as you can. Stateless. So one person makes a prediction, it doesn't affect somebody else. The fact that you gave me an image which happens to be a hot dog does not mean that my answer to you who gave me an image which is not is going to be any different, right? So I can discard the state between those different runs. It's elastic, so sometimes nobody is using it at all, hopefully about 4 a.m. when all of the late night folks have fallen asleep and before the rest of the world wakes up. And then, lunchtime comes around and boom, you get a huge spike in your usage, right? And of course, there's multiple users. So I've got people all across the world using this from all kinds of different systems through my API. This is kind of like running an OS, right? I've got the scheduling considerations, I've got the elasticity considerations, I've got to be able to run on heterogeneous hardware, all of that kind of thing. What's appropriate for each of these situations? Raw metal or a virtual machine is great for training, so you've got your own NVIDIA setup at home, you're running lots of cool GPUs on your big tank that you've built, or you're renting out VMs for the period of the training time that you need. Works wonderfully for training. For inference, though, we're going to start with a different model. We're going to say, okay, containers, first of all. So what do containers give us? Well, they work great in a stateless environment because you stand up a Docker container, you do the inference, and then you can destroy it whenever you want, and you don't care because you don't have to preserve that state. You've got short compute bursts. So each one of these can satisfy each of those different calls, and then you're done with it. We want to add elasticity to that. And so we need a way of managing our Docker containers, right? Of saying, okay, I need to stand up this many instances at a given time, and when they're not needed, I'm going to scale back down. So we're going to add Kubernetes on top of that for our Docker management. And we need to be able to handle multiple users. Now, yes, of course, this is running in a multi-user system, but realistically, what I mean by multiple users here is that anybody writing an application in any language, anywhere, can go and access that particular model. And the way I'm going to do that, of course, is through a REST API, because that's agnostic to all languages. Microservices is this design of a system as these independently deployable and loosely coupled services. That works great for what we've got so far. These are maintainable, they're scalable, software and hardware agnostic because they're inside a Docker container. I can have rolling deployments, so when I version that model, I can just say, hey, next time you have a call for this particular model, use this Docker container instead. And so I don't have to worry about destroying everything all at once and saying, pause, I'm going to reinstall my server. It's just that the next call that comes in, boom, new version, as needed. Serverless, the encapsulation and starting and stopping of these functions per request, and adding a just-in-time compute model on top of that. Give me elasticity, gives me cost efficiency, and it gives me great concurrency, and in an interesting way, improved latency. And I'll show you how that works in just a second. So, first of all, let's talk about cost efficiency, right? So this is your standard model for how am I going to satisfy all of those users that come along at noon, and that's my peak load, right? So you look at some abstract graph of usage over time, and if you really want to make sure that things don't crash and burn and people stop getting responses, you of course have to plan for that maximum load. So I've got to have as many servers as necessary to satisfy whatever that peak is going to be, all running, ready to go. Okay. Now, I can get a little bit better than that, and I can say, okay, what if I start and stop virtual machines at a given time in order to be able to satisfy that predicted load? So I can add a little bit of a management layer on top of that and say, okay, when I see my first VM starting to get full, I'm going to spin up another, and I'm going to load balance some of the requests out to that. This works pretty well, but it's fairly staggered, right? In some cases, you've got minimum 1 hour billing times on these. You've got delay as you need to spin up the VM, so you have to predict for that pretty heavily if it takes a lot of spin up time, etc. What we see in the customers that we've looked at is that in many cases, you're talking about a 50% cost savings or a little bit better when you start moving to actually managing your VM stepping. Now, there's some DevOps work that has to happen there, but it does help. Great. But let's get tighter to that curve, right? So the green is our actual provisioned availability, whatever computes are available to do what I need. The line is the actual usage at any given time. With serverless, you get down to this, right? Your actual availability at any given point in time is just a teeny tiny bit over your actual usage at that point in time. A tiny bit over because you have to be ready to immediately bounce, have another container ready to go when somebody else needs it. But once you start moving to this kind of model, where you're really just instantiating small individual Docker containers for each individual model that you're going to execute, you get very, very tight to this curve. And you're talking a sixth or an eighth of your initial costs of what you're going to have to do with virtual machines. All right. Concurrency, of course, right? So the big thing about this is that because those Docker containers are stateless and because I can just simply duplicate them, when I have a whole bunch of requests coming in from different people, I'm just standing up as many as I need simultaneously. I can even have heterogeneous models and those different things. They're all going to run at the same time. Load balancer's just going to switch between them. Pretty obvious stuff. Low latency. Why? Because we've got great infrastructure now, right? We've got great cloud providers that have data centers all across the world. When you're talking, say, 50 milliseconds up to half a second for a prediction, so those slightly lighter weight models that run pretty fast, the latency to get from, say, China to West Coast US, where we happen to be, where some of our data centers are, the latency dwarfs the actual prediction time, right? So that user's experience becomes very, very poor. But the great thing about these data centers is when you have a nice containerized model that can be immediately copied to any layer of this to any part of this system, and it's abstracted out properly, then when you see that I'm starting to get more users in China spinning up, you just say, okay, hey, go ahead, pull all those containers over there in that data center, start spinning that up. They're getting 15 millisecond latency at worst, and all of those users are getting satisfied requests very, very quickly. So you're actually improving the user experience by just taking advantage of the infrastructure that's out there over an abstraction layer that makes it really easy to do that. Okay, other things that you need. So we're most of the way here. We're doing pretty well. There's a few other things that are a little bit tricky. GPU memory management is a bit of a problem. Getting multiple things running on the same set of GPUs. Sometimes the memory isolation is hard to manage. Sometimes things will request more memory than is actually available, that sort of thing. So there's some tuning you have to do, and I'm going to hand wave on this because it's a big discussion in and of itself. Job scheduling. Right? So knowing how to predict what that load's going to be, knowing how to stack things properly in the right space. Because even though these are all individual Docker containers, they're still really physically running on some machine somewhere. And you've got to do things like say, well, I have requests for these two things that are going to use a whole lot of GPU. And then I've got a request for these other couple things that don't use a lot of processing time, and it's only CPU, and they don't need much memory. So it really makes sense to stack that bundle together, and then have another machine warmed up and ready to go for when more GPU request comes in. So there's a lot of tuning you have to do to make this all work well together, but it's possible given time. And cloud abstraction, right? Because we really don't want to be tied into a particular provider. I'd like to be able to take all the stuff I've written, all the models I've got, et cetera, and when it becomes cheaper to run on one cloud provider than another, to just be able to pick the system up, move it over there, and have things seamlessly continue to run. Again, when I'm writing a file, I don't want to have to be thinking about, am I writing to a network, am I writing to a local disk, am I writing to this particular model of hard drive versus another, right? We want to be at that level that DOS is at over hardware abstraction, but we want to do it over cloud providers. So this gives us sort of a scope of what we really want in an operating system for AI, kind of all the little moving pieces, right? I'm going to add one more thing on top of this, though, because really everything I've just talked about, that's the kernel, right? That's the core of the operating system, your elastic scale, your runtime abstraction, your cloud abstraction, yeah? But think about an operating system. What's on top of all of that? Hopefully a nice UI, where you can do things like see what's actually available in the system, pick them out, discover them, try executing them. Instrumentation, monitoring, logging, etc. Authentication on top of that, all those other little bits and pieces. So I'm just going to call that the shell and services layer, right? And that's got to sit on top of it. Okay, so how does this work in reality, like actually in production? Someone comes in as a user. Now, if they're making a request for that shell layer, something like, hey, tell me about all of the models that you have available and what they do. Well, generally speaking, that's a web request. I'm serving some web page out, right? I shunt it over to my web load balancer that's closest to them. Pretty standard stuff here. My web server there serves up the right web page in whatever framework, tells them the information they need to know. Okay, they come in later and they start executing some API requests. These come in, I hit my API load balancer. That picks the API server in the right cloud region closest to them. It goes to a worker. If there's one already spun up with that model hot and ready to go, it just hits it. If it's coming in and another one needs to be spun up, it's going to make another Docker instance, bring it up, shunt them over to that. Of course, it always stays a little bit ahead. So in reality, I'm spinning up those new containers before the requests even come in. I get efficiency and low latency here. Okay, what about composability? So I talked a little bit about Unix, right? And this ability to pipe from one thing to another. I can cat a file, get some results, I can pipe that over to grep, filter out just the stuff I need, do a word count on it. Suddenly I have a count of all of the lines in a particular file that contain this word. But I haven't written any novel code here, right? I've just said all these bits that are there, just pipe them together in the right way and give me some result. I want to do that with machine learning. So somebody out there maybe has already written a fruit classifier. I give it any piece of fruit, and no matter what it is, it'll tell me what kind of fruit that is. Hand it a banana, great. Hand it an orange, it's an orange. Hand it a piece of broccoli, crap. Okay, because it's only a fruit classifier, right? Fortunately, this other guy has a veggie classifier out there. Same thing, but in reverse. Hand it broccoli, good. You know, hand it an orange, up, I've got a problem, right? Very simply, I want to be able to stand up another algorithm on top of that, which says when an image comes in, pass it to both of those. Whichever one comes back with the highest confidence and an actual result, hand that result back to the user. So now I have a fruit or veggie classifier. I've done nothing here but write a teeny tiny bit of code that joins those two together and looks at the results and hands back the relevant thing. Obviously, this is a very simple pathway, but you can imagine that you can do a lot more complex things with this. Like once you have this pipeline ability, you can do things like you're looking at a video stream with some audio input. Okay, take some images out of that video stream. Take the transcription of that audio, transcribe it on the fly. Look for keywords in the audio that match to images that I have detected through my machine learning model, which are actually in the video. So now I can start to think about things like, hey, this person is actually talking about this particular object in the frame right now, and maybe highlight it. And that's just by pipelining existing models together with a little bit of glue code. And if I need something else more specific, I write my own classifier, I stand it up as a model, I add it into the pipeline. But it's all very easy to work together. Okay, once I've got that, I add my intelligent orchestration on top of that, so I can start looking at things like not just how to stack those efficiently in terms of making all the resources available, but I can say things like, well, when someone calls this algorithm, it always ends up pipelining down to this other one, right? I can start to see, just by inspecting the history of what's occurred, which models tend to get spun up at the same time. And that might be because they're directly in the pipeline to each other, or it might be because the end user's application tends to hit this API endpoint and another one. Either way, once I start observing that, I can start intelligently orchestrating which things I'm going to need ahead of time, so everything's stood up in the right location, the APIs people are going to use at the same time are co-located within the same data center, so they're quick to talk to each other, and so on. I start getting huge efficiencies on top of this. And of course, this all occurs with an idea of runtime abstraction on top of it. So that fruit classifier might be written in Java. That veggie classifier, it might be written in R. My glue code to put them both together might be in Python. I don't care, right? You pick the language you want to work in. or you pick the language that's best for the particular model, the particular framework that you're trying to use to do whatever you want. They're all operating in their own independent Docker containers. I don't have to think about dependency graphs between them, because each one is just going to talk to the other via an API, and it's all going to orchestrate smoothly together. Same way that applications, no matter what you've written them in, once they're compiled down to a locally executable binary, you don't care. You just pipe them together, right? OK, and then lastly, this idea of cloud abstraction, right? So going back to the example of storage, when I store something in S3, it's a particular set of API calls which has to occur a certain way. When I store something in Dropbox, it's a different set of API calls. When I'm storing something to a local file, it's a different set of calls, right? But let's get that all standardized. So literally all you do is you say file, and you give it a URI, and the abstraction layer says, oh, I recognize that URI. It starts with S3://, so I need to do all these S3 calls in order to connect down and find and use that file. But the only thing that the developer actually has to change is that URI of the file itself. They're not worrying about all of the underlying concerns. And you're doing the right stuff, like buffering files in the right way for whatever channel they're coming from, so that you have a single unified and usable file API on top of it. So there's a ton of little things like that. You can imagine all the other stuff for the different resources that has to happen. But you bundle it all up, you make a nice abstraction layer on top. Okay, and then you find yourself able to do this, with your compute, with how you manage your auto scaling, with how you do your load balancing, et cetera, so that you can take that same system, you can put it on AWS, you can put it on Google, you can put it on Azure, you can run it in an air-gapped environment on OpenStack, whatever you want. Your data science team does not care. They're just writing models, putting them out there, and writing little bits of glue code. Okay, and then looking at that shell, looking at discoverability, using the App Store as a model, what we chose to do was make a system in which, whenever a data scientist builds one of those models and puts it up there, they fill out a little bit of Markdown, and this then makes it available inside sort of an App Store for API, where I can, for AI, where I can go and I can search and I can find what I'm looking for. I get back a description of all of the algorithms that might match that. When I drill down into any one of them, I get a bunch of useful stuff, like I'm able to see the full description of that if I want to. This one's thin. I'm able to execute code samples in any language. I'm able to really try it out right there before I decide to integrate it, right? So, stack agnostic, composable, self-optimizing, auto-scaling. Monitoring and discoverability, I'm not going to talk about a ton here, but you get the basic idea, right? You want to be able to see what's happening. You want to see what models are being called. You want to be able to see whether there are errors on any of those, all that kinds of things. That's built in too. And then I look at where am I? Well, it's pretty good. We've made a lot of advances here. We're not where we need to be. When you look at the overall state of AI, I'd put us a lot more on the left side of the graph right now in terms of overall what systems are common, what systems are available. But we believe that this is one step forward, and we're hoping that there's going to be more and more movement around this concept, and then eventually we'll come to a common agreement. Right now, what you've got, if you go to algorithmia.com, you have one implementation of this, right? Which I think is a pretty good one. Surprise, surprise, I work there, so yeah, I'm a little bit biased. But what you can do is you can go in, you can discover the stuff that's there already. Everything's categorized and tagged and rated, very similar to the App Store, right? So you can actually drill down on certain tags. You can see other people's reviews of particular models. You can read through their description maybe of what research papers it comes from, what the inputs and outputs should be. You can go ahead and pick up a code stub in just about any language. You can also, of course, access it through a raw post if you want to. But the nice thing about the code stubs, the reason that we created those, is we really wanted the syntax to be very similar no matter what language you're speaking in. So of course, within the constraints of that language, the way that you access a file is almost identical, for example, across all of the language APIs. So it's now very easy to understand, very portable. You can go in here and you can literally just copy a snippet in whatever language you want, drop in your own API key, and boom, you're off to the races. You're actually executing that model remotely. Everything is auto-scaled, elastic, secure, individual isolated containers. and managed to maintain that 15 millisecond total overhead latency. I think we've actually brought it down a little closer to 10 now. And then if you are a data scientist, you have this capability of going in and actually adding your own model. So a whole bunch of languages that we support, including some newer ones like Rust, for example, but of course all the basics, Scala, Python 2 and 3, R, etc. Just about any framework you want to use in any of those. As soon as you put that model up there and you publish it, instantly JSON API that anybody can access, or you can say, hey, I want to publish it privately so that only I or only my organization can utilize it. So this gives you the capability of actually developing in-house models and not exposing them to the public, but using this machinery to run it across your organization nonetheless. You can call other models seamlessly regardless of their language, as I was just talking about with the sort of pipelining capability. Granular permissions, so you can say, hey, this is my organization, they're allowed to access these algorithms, or even creating API keys that are specific to just one or two models in specific contexts. So you can say cores it to a particular domain if you're running out of JavaScript, for example. GPU environments are available. So when you execute a serverless function, this is fairly unusual in the industry right now, you actually have full GPU access there. So you can run GPU-enabled TensorFlow right in a serverless environment, which is amazing. And we've got long run times on those as well. So those models can actually run for up to 50 minutes in prediction mode, right? So you're not limited to that 5 or 10 minute maximum that's often available on serverless functions. We thought about the fact that certain things like deep image inspection, et cetera, are going to have to run longer. And I want to give you a specific example of this just to kind of show you some of the fun stuff that we're able to do right now. So this is a fairly simple, individual image transformation. This is, data science 101. Oh, well, not quite, 102 at this point. But take a black and white image, you've trained up a data set, you want to go ahead and colorize it. So this is just JavaScript running right here. You can't see that because I didn't switch to the right screen. So sorry. Here we are. So this is just JavaScript on the front end. There's nothing going on in the browser except your basic, like, render the page. When they click an image, go ahead and make an API call, right? So I'm going to click on a black and white image that it's never seen before. It sends it off to the API, runs the colorization. I get back a result, which is, not bad. There's a few little problems, some edge detection not quite working at the top there, but on the whole, yeah, pretty good colorization. But I can go further with this, right? Because remember pipelinability. So I've got a bunch of models out there that'll do various things to images to transform them in some way, right? Well, what is a video except a series of images, right? So shouldn't I just be able to take that video, break it apart into images, run those image transformations on each individual frame, put them back together, and have an output video? Sure, you can do that, and it works. So I'm going to take this black and white video it's never seen before, reassemble it, and I get a color output from that, right? It's just trying to figure out what the colors are. There's a little bit of a problem with this motif in that you see there's some color flicker and that sort of thing because it's not doing any interpolation between the frames, but it does work, right? It demonstrates this idea of pipelinability. And to just show you a little further, there's other stuff, like there is, say, a deep style, which basically stylizes an image, right, according to some template you've created. That's, again, it's just a single image transformation that exists in the system. But I just take that same glue code and I just simply swap out which algorithm am I calling for each individual image, and now I've got this thing that will, hello network, thank you, that'll transform this image and stylize the video output, right? Same thing with, say, saliency, which tries to track images in the frame and show you what's most important or what's moving, etc. Or maybe I go and I do video metadata extraction, right? So an object detection algorithm, right, just takes an image and it looks it over and it figures out, hey, this is a car, this is a boat, this is a person, etc. Why not do that over a video stream? So I'm going to take, this here, and I'm going to say use a specialized object detector that's been trained up, which identifies the make and model of just about any car, right? So I'm going to take this video, I'm going to run it through the car tagger. It's running this on each individual frame, but then when I assemble the output, instead of creating a video stream, as I showed before, what I'm actually doing is I'm creating a JSON stream here, so a bunch of time-stamped JSON results, each of which tells me what things are in the frame. So I can go to any point in time, and I can say, right here, I've got a Hyundai hatchback, right, that has to be showing. And I can construct a timeline of all the objects that have been demonstrated over the course of the video. And then there's a little bit less visual stuff. But this is the data source here is construction permits issued in different cities over different years, right? So I can take that and I can do some basic time series filtering on that. I can go over to Boston and I can say, hey, let's go ahead and let's filter all of that with a seasonality removal and a simple moving average. And that's going to give me a forecast of what I will expect for permits in the future in that particular city, et cetera. And all of those changes, as I change these different filters and whatnot, they feel relatively native to the user, right? Like this is all reactive and it's moving smoothly, but every time I make a change, it's taking that data set and it's running it through another machine learning algorithm that's just responding quickly on the back end. So this is the kind of power you get once you have that kind of system behind you. So with that, I will say thank you very much for having me here. Thanks.